And let us today discuss the important ideas related to the compactification of extra dimensions in string theory. And these ideas originate from the so-called Kaluza-Klein theories. And this reminds me, before we do physics, Mr. Kaluza, I have forgotten his first name. I read it but forgot some years ago. He was from Lower Saxony, Niedersachsen. Mr. Kaluza was from Niedersachsen. And this Kaluza-Klein theory, it dates back exactly 100 years ago, exactly a century ago, around 1920. So, and Mr. Einstein had recently published his general theory of relativity and had become famous. And this great friend of mine, if you could somehow David Hilbert, he was the mathematician par excellence, a great seat at Göttingen. And this guy, Kaluza, eventually ended up as a professor in Göttingen. So, in those days, writing down the Einstein equations in the covariant form itself was a huge task. And David Hilbert, my icon, in fact, he was the first one to write down the Einstein equations in the covariant form. 1 week later, Einstein presented it at the Russian Academy of Sciences in Prague. Anyway, that's a different story. So the point is, Einstein was very impressed with Mr. Kaluza, and he encouraged him to work on this. He was trying to unify the four-dimensional theory with one extra dimension as a circle, and trying to see if he could unify gravity with electromagnetism. Of course, it did not work in the manner that we would call it a successful unification of gravity and electromagnetism. But nevertheless, you see, this idea of compactification of an extra dimension was really great. And string theory was not even born at that time. Nobody knew about what was string theory, or there would be some. It had to come much later. Actually, not to talk about string theory, even field theory was in the infancy stage at that point of time, 100 years ago. So field theory was developed in the next couple of decades after 1920 or around that. So the entire advent of quantum theory begins with Mr. Planck, and that is exactly 1900 when he talked about this quantum theory in the first place. Then quantum mechanics, quantum field theory, everything, and then now string theory. So let's briefly recap. I would tell you in a very compact fashion, because I always run short of time. So yes. So let me briefly recap the idea of Kaluza-Klein. Let us catch that particular point. Okay. So Mr. Klein happened to work in Sweden, in Stockholm somewhere, and Kaluza happened to work in Niedersachsen. Anyway, so that was 1920. Okay. Now let me quickly introduce a scalar field phi. Let me define it by the capital phi, and let me say that this is a function of f phi And this I want to so let us consider a theory in 5-dimensional space-time manifold, okay, and flat space, no curvature, okay. So, and this field capital phi happens to be a function of these arguments, including x of phi, whereas phi m, which is denoted by small phi, phi m, is a function of t and x. So, and this we separate out. I am x phi by r. So essentially, what are we doing? We are making a Fourier expansion of the field capital phi, and these are the Fourier modes. Okay, phi m are the Fourier modes. Okay, m would be an integer; it will take values 0, 1, 2, 3 up to infinity, and therefore I would have infinite number of Fourier modes, and phi 0 would be my 0 mode. Okay, 0th frequency mode would be phi 0. And now what we do is x phi we define as x phi plus twice phi r. Okay, so we compactify the 5th dimension x phi along a circle of radius r. Okay, so it could be given. So this is a coordinate on a circle, on the circle. Radius r, and of course t and x are the coordinates of the 4-dimensional manifold. Okay, so t and x they span the 4-dimensional space-time manifold, and this 5th dimension is being compactified along a circle of radius r. Now, what would happen? Now we could write down the equation of motion, and this would be, let me say, in 5 dimensions, capital phi p x and x phi, this equals to 0. Usual the Klein-Gordon equation. These are massless fields. They are massless fields, and so this is the equation. And here, or let me write 0 equal to this, and this I could write as minus del 0 square plus del 1 square plus del 2 square plus del 3 square plus del 5 square. That's fine. And this I could write as, this is my usual, so if you like, you can denote it for the time being by 4 in the 4-dimensional D'Alembert plus phi. Okay, and now del 5 square phi, in particular, this would be, I have erased this by mistake, I would get iota m by r whole square times phi m. So you differentiate it once, you get once this factor, you differentiate it twice, you get this factor twice, and this is obviously equal to minus m square by r square times m over this. And so my equation of motion is therefore this equal to D'Alembert minus m square by r square capital phi, and so you see this is the here it goes it is in the 4 dimensions. Okay, let us not spend time on that. Now, so it is exactly this equation, and by if you put the value of phi m here, and this is non-zero, so basically what you get is phi m. Okay, what you get equation of motion as this, and these are the equations. So let me here mention for the modes phi m, and these phi m's are functions of t and x and not x phi. So